Hey, this is Chris Linus from NASA.
Or just mute them.
So I want to thank everybody that's been willing to stick with us through this. We've had a major electrical storm here, which has knocked out power from where we usually run this telecon. So we're now running it from Goddard instead. We may even be on backup generator power here. Hopefully it'll be enough to get us through to the end of the hour. What we're going to do today is talk about a new development, relatively new development in data analytics called data cubes. And I was first really exposed to this at the recent WGISS meeting in Annapolis. I went in being a little bit skeptical of them, but what I saw in some of the presentations looked really interesting. And so I asked for a couple of the leaders in this area, Rob Woodcock and Brian Killough, to give us a little bit more detail on exactly what data cubes are and what kinds of uses they can be put to for end users looking to do data analysis, particularly data analysis on really large data sets. This is really getting into that big data space that a lot of us have been moving to recently. Okay, so we're still signing on. Okay. And so what we're going to start with is, I think Brian was going to give us a first sort of a high-level view of what data cubes are and talk a little bit about some of the implementation aspects. And Rob Woodcock was going to take us more into some of the areas of usage for our data cubes. And now, just bear with us while we set up the telecon to turn over to Brian. Just hold.
Thank you, Chris. I appreciate the intro. As many of you know, I work for NASA Langley, but my full-time job is to lead the CSIRO Systems Engineering Office. And one of the initiatives that has taken a large portion of our work within the last year is data cubes, and I'm going to tell you a little bit about those today. The problem that we have, many of you are aware that there's a significant growth in the quantity of land imagery. Since the release of Landsat in 2007 and now with the new Sentinel missions, this example you see here is just the data growth for Kenya, but it is quite typical of most developing countries, countries in general. So in the particular case of developing countries, they often do not have the knowledge or the infrastructure or the resources to deal with the data. So they have issues with accessing it and with utilizing that data. So through CSIRO, we have received a number of requests, whether it be directly or indirectly in some of our interactions with these users, and they have told us that they need help. They need help in order to take advantage of these new volumes of data. And what we stumbled upon was something that was working quite well in Australia, and that was the data cube technology. So we have now spun that into something called the Open Data Cube, and I'll tell you a little bit more about what that initiative will be. So first off, data cubes, for those of you that are not familiar, to simply put it, it is a stack of spatially aligned pixels. So if you think of the cube as having dimensions of space, x and y, and time in the third dimension, you can stack these pixels together, spatially aligned. They can come from different data sets. They can be all from a single data set, but it could be a way in which to manage large volumes of data together. So we get away from the traditional scene-based file structure, which differs from agency or from satellite to satellite, and if we can pull it into one common structure, we may have a half a dozen different data sets all within this same common structure, which allows us to use a common set of tools. The approach that we're pushing is for analysis-ready data. We want to reduce the processing burden on the users. We want it to be open source so that everyone can get access to it free and open. And we certainly believe that it can exploit time series data and large data sets. So our users have come to us within the last year or two and expressed a lot of common desires. And I've already mentioned a few of those about minimizing the time and knowledge for preparation, free and open source solutions, time series analyses, multiple data sets, common GIS tools. There's a bullet here about owning the data. We have found that many countries want to have that data locally because of either a lack of internet or a desire for them to take some ownership over the final products and to build capacity within their country. And they also want some customer support. They want some help to get this going. So our goal in all of this is not to sell a product or to push a tool on anyone. We really want to come to them with a solution, and that's where we think the Data Cube has the value. A little bit about our vision for where we see this going. So we took what was happening in Australia through the geoscience, the Australian Geoscience Data Cube. Those of you might have heard of AGDC. And we came up with an open data cube concept that is not tied to any one country, but we want it to be a global solution that a community could be built around that. So agencies in CSIRO were excited about this because it's an opportunity for them to feed this open data cube engine with analysis-ready data products. So that's a big initiative now in CSIRO, is to get all that pre-processing done in advance. We want our customers or our users to feel that they're the focus of all of this. So in the end, we want them, when they talk about Open Data Cube, that it is a brand name or it is a solution that they can know and trust. And by doing so, we hope that many countries will be able to work together on this. We have a target of 20 countries by 2022, and I'll tell you a bit about that, where we are now. Certainly a lofty goal, but one that I do think we can achieve, and we're working quite hard to get close to that already. Our key partners, if you've heard of GEO and World Bank, I'm sure many of you have, they're very interested in all of this. GEO is all about exploiting Earth observation data, not just satellite data, but a much broader vision. And the World Bank we see as one of our capacity building partners, and they certainly have an interest in this. To show you a few examples of where we've been successful, we've been working closely with Colombia for the last 2 years. They now have a full country-level Landsat data cube. Every Landsat scene, 25,000 of them, going back to 2000, is now ingested in a data cube. They're using that for forest mapping and land change detection. It took us a little while to build that capacity, but we really think it's been a great success story, and we're going to continue to work with them. The other end of the spectrum is a country like Switzerland. They came to us with a large amount of expertise in dealing with technology, both computing technology and with satellite data, but they were interested in how the data cube could provide them advantages of combining multiple data sets together. So we worked with UNEP Grid in Geneva and got them moving. They have made rapid progress almost entirely on their own, but we certainly do provide some consulting along the way to help them with troubleshooting. And they are now in the process of expanding the data cube to Moldova and Georgia, which are 2 countries that they have a capacity building interest in. And Switzerland is going to take care of all of the installation in those 2 countries without much of our help. So it's an example of an expansion sort of organically. Here's what it looks like in our Road to 20, as I call it. If you look at the dark green data cubes, the cubes that I have here, Australia, Colombia, and Switzerland, those are the 3 operational ones. We have 4 under development. The United States is working on a project called LC Map to basically put all of the Landsat data in a data cube format, and we're working with them so that we have compatible systems. You see a cube there in Uganda, one in Vietnam, and another in Taiwan. All of those are in development, and I expect those to be finished probably within the next year. Those in red have expressed interest, and we are communicating with each of them. So as you see here, there's 23 on this list right now, and it tends to be growing all the time. So we're looking to continue this expansion. So now I'll show you a little bit about what products can come out of the data cubes. We have an online tool on the cloud on Amazon right now. The URL is at the bottom, and I will repeat this at the end of the presentation. On this Amazon cloud are 15 data cubes. They're all fairly small in size, but they're meant to be that way so that you can do some rapid prototyping and analytics. There are 7 applications, everything from cloud-free mosaicing, fractional cover, vegetation indices, water quality, and you can also output geotiffs as well as GIF animations. This entire tool is free and open, and it gives people the ability to test the data cube, what its potential is in a hands-on demonstration. We've had great success with this. When we bring a new country into this system, the first thing we usually do is we take a small portion of their country and we create a cube, a sample cube, and we put it onto this Amazon web cloud, and that gives us the ability to let them test it and become familiar with it, and it builds a little bit of success, but it builds some confidence in that they're going to be able to do this on their own. So let me show you now. This is an animation here over Lake Chad in Cameroon, Africa. What you're looking at is a time series generation over 17 years of the existence of water. And as the colors change, what's changing is the fraction of time that pixel is water. Anything that is dark purple is water 100% of the time. And as you see in regions, if you highlight here on the western side, these areas here were covered maybe 10 or 20% of the time. This was actually an area that was flooded in the latter portion of those 17 years. And in some of the areas here, these are very small, 1 to 5% periods where there was water existence. So this is a very interesting application. Water detection through a thick time series of data gives us an amazing amount of information of where did water exist, for how long did it exist, and what can this teach us about possibly future urbanization or future agriculture and where we want to go. Here's an example over Australia of Lake Burley Griffin. What you're seeing here is a transect plot, and you're going all along this line from left to right through this lake and looking at water quality. So the water quality goes from blue being very clean to red being less quality. And what you see here is a axis in time and then the transect axis across. And what has happened is right around the year 2000, you notice the difference between more red features. So there was less water quality, or it was more opaque and the visibility was substantially less. And then at about 2000, they started a clean water project in this Lake Burley Griffin, and you notice now the increase in blues, which is cleaner water. So it's not so worried about the actual numbers, but what you can see is the scale of the change is easily detectable. We certainly saw a change around 2000. Next is fractional cover. This is really important for the agriculture community, and what you do is for every pixel, you estimate through an interpolation algorithm the fraction of bare soil in red, photosynthetic vegetation in green, and non-photosynthetic in blue. And what you see in this figure is a lot of bare soil in the regions outside of the lake. This again is this lake over Cameroon, Lake Chad in Cameroon, Africa. Along the inlet river here, this is the Chari River, the closer you get to the lake, the more green you would expect to see, and what you're seeing here is high vegetation, and you get also some deadwood vegetation here in the blues. And that often occurs between the transition of the bare soil and the vegetation, because this is older vegetation that has been sitting there. This is a very commonly used product for agriculture. So let me show you an example here. This is agriculture change. Now think about that same product you just saw, fractional cover, and now what we're going to plot here is a time series of fractional cover for this one pixel in the middle of the screen. And what you see here as you go through time, this is a seasonal variation up and down. And in this particular plot, as it got out to about 2003 or 4, something happened. And what you see is that it became a grassland area that had a lot more green vegetation in it from about 2004 onward, but prior to that, it was just cycling through the normal seasonal variations with a larger amount of bare soil and less greenness. So a change, certainly a change in the agricultural land at that point. You could do this pixel by pixel. All this time series data exists, and it's down at any resolution you desire. NDVI anomaly, this is vegetation index. This is also quite common. Those of you that are familiar with the GeoGlam project, they use something called a crop monitor, but they do it at MODIS scale, which is 250 meters. This now allows you to do the same type of product, but at a Landsat or Sentinel scale, which could get you anywhere from 10 to 30 meter resolution. Significantly more information, but now that we have the time series, you can build an anomaly. And the anomaly shown here is comparing a single scene in April of 2016 to the same April months of the 3 years prior. And what it's showing is there was more greenness near the lake and less greenness near the mouth of the river in this case. The last thing I'm going to show you here is an example of land change detection. This is some of the most exciting stuff that we've seen thus far in terms of the power of the data cube. We're investigating two different approaches right now. There's an algorithm called CCDC, which was created by some researchers at WGISS and Boston University. We've now converted that to a Python script, and we're also working on a new project with BFAST, which is Wageningen University in Europe. And what you basically see here is the scene on the right is the background scene, and what it does is it goes through the entire time series, left to right here, and it looks for a break in the time series that signifies a change. Typically what you're doing is you're looking at one or two spectral bands, you're curve fitting those spectral bands to the seasonal variations, and then at some point in here, it doesn't take into account outliers, that's all factored into the algorithm. There's a break, and we call this break some change, and notice what happened here, the variation is more significant, and there's been a land change in this particular pixel. So that's just a single pixel. Here is the entire image, and what you get is a count of the number of changes. I'm going to show you what it looks like in a larger scale. So here's an example here in Vietnam. We did this recently for the Vietnam data cube. There's a mosaic on the left. That's a cloud-free mosaic built up of probably a year's worth of data so that we can screen all of the clouds. And then what we did is we ran the time series change detection over 16 years for this entire scene. And what you see in the top right is the scale. Anywhere is medium green is 1 change, 2 changes, 3, 4, and 5 is the red. There's a few of those scattered. Most of what you see here is 2 or 3 changes, and those are distinct land changes. So something has happened just to the east of this lake, and what has happened is an urbanization. This entire area in that 17-year period was cleared, and a lot of urbanization had occurred. The regions you see outside of the lake, which are rather sparse, may be deforestation. It might be any number of changes. It could just be a change in the foliage, a significant change in foliage that occurred. So what we did was we compared these results to Global Forest Watch, which is a very common product. This one is done by Matt Hansen online. Many of you might be familiar with it. So if we take a Global Forest Watch scene for 15 years, this is the product from Matt Hansen, and this is the product on the right-hand side from our PyCCD. Now you have to remember the differences between the two. Matt is only looking at forest loss, so what you see on the left panel is just forest change, but what you see in our results are all of the land change. That could be anything from urbanization to grasslands changing to something else, but it has nothing to do with, it could do with forests, but it doesn't have to be. So you will see a lot more suspected change, but what you see is the patterns of change very much are in line with what you're seeing in the Global Forest Watch. The locations and some of the actual physical patterns, you can see this little portion here in the bottom right, which goes along with that spot there that I'm highlighting on the screen, and the lake region here as well. So this whole thing takes a long time to execute, but by having it in a data cube, the actual execution performance is significantly better than if it were in a stack of scenes. And we're starting to do some of that testing now. So here's a few more examples just to show you. There was a case here. These are in Colombia. There was some possible deforestation here when they cleared out for a road. You can see that in the figure. This is actually a reservoir in Colombia that they know was built in a 17-year time period, and it's very clear that all of the land change occurred with respect to that reservoir. So they completely created that reservoir out of the forests. And so that's all I have here today. If any of you have a desire to check out our website, CSTorg is just for CIOS. We have an Open Data Cube website, which is being revised right now. We're working hard to get that in place, and the Amazon demo is the very last link. Thank you very much.
Thank you very much, Brian. That was great. So now we're going to go to Rob Woodcock from CSIRO in Australia, who's going to give us a little bit more, I guess, detail and insight into what's going on in those data cubes.
Hi,
Rob, take it away.
You can hear me okay?
I can hear you. You're a little soft.
Okay, let me see if I can figure out what's causing that. Has that a little bit better?
That's good.
That's way better.
Excellent, Rob.
Okay. My apologies. I've had to reconnect since we had the lightning storm, via an entirely different connection through my iPad rather than through my PC. So something to be aware of, Jennifer, is I actually can't advance slides at the moment, as far as I can tell.
Okay. So.
Okay, if you want to just tell me next, that would be fine.
Okay, I will just tell you next. So, all right. So, thank you, everybody. I'm Rob Woodcock from CSIRO. So, I should just let you know I've been involved from the Data Cube since the tail end of version 1's development. We're now sitting on version 2, which is a fairly significant change from the version 1. And our interest in the Data Cube in this particular presentation will be talking about the CSIRO perspective as opposed to the whole of Australia perspective. So we have a number of initiatives that we're building on top of the Open Data Cube, and the Open Data Cube is the broader, more holistic initiative that underpins all of these activities. In the interest of time, I'm going to skip the background information around CSIRO's applications, and so if you could just jump down to slide 8, it's the one with the big green shaded thing and some boxes on it after the question mark. A little bit further, yeah. Okay, thank you. All right, so the types of applications that CSIRO does are very similar to the ones that Brian's just outlined. We do a lot more work on water quality and so forth, but all of them involve the researchers in CSIRO and ultimately our end users in government and in industry going through this workflow of data from obtaining access to appropriate Earth observation data through doing any corrections that are necessary to that. The amount of processing that's required at that early stage to get to a reflectance in the case of an optical product, for example, that is required there. It depends a lot on the supplier as to whether or not we've got raw data coming off of instruments or in fact already processed data. Then there's a pile of information extraction algorithms. These are fairly generic ones, things like doing math, adding up, dividing medians and so forth that are done. In all of our applications, some level of access is required. Most commonly these days, that's some form of web portal displaying some of the information or the resulting products in there. And of course, ultimately, this is all about producing information products for some form of decision support, usually in most cases. So this flow is what we're dealing with all the time. In practice, the diagram is nowhere near as neat and tidy as that. It's actually a mess. There's lots of data providers. There's all sorts of algorithms involved. There's an inordinate number of files that need to be managed. And as the volume and the velocity of the data that we're getting from the new sensors is coming online, and Brian showed a lovely graph of just how much that is increasing in the last few years, as that's gone on, become the case, the mess that underpins this very simplified diagram has become very unmanageable. It's actually a lot of heavy lifting, and the important thing to note about that heavy lifting is everybody's having to do it. And so within CSIRO, we find that people are actually everybody's repeating this process over and over again. They're repeating all of that stuff in the middle in particular, and it's undifferentiated. There's no real difference between the way in which people are approaching that, aside from personal preference on tools used, and so a lot of that is becoming prohibitive. So it's dealing with this middle section that's pain and suffering for everybody. That is really our objective with the data cube. Can we get it so that you can still build your own types of information products? You can still, in our case, for our CSIRO scientists, we still want them to be able to produce their own algorithms. And so they're still doing their research into the information products, but they're not having to deal with data management, high-performance computing, cloud computing, distribution of tasks to run in parallel to get the job done reasonably quickly. Try and bury all of that behind magical code so that in their world it's a case of, this is my math, I'm going to run it on a big computer, push go, and it just happens, and the thing will actually parallelize itself and make itself running. So that's a type of aspiration, make life easier for our scientists, which in turn will accelerate the ability to move our new algorithms out to industry and government use. So if we go to the next slide. So the way that operates in the data cube is we deal with this midsection. So this is a diagram of the external interfaces to the data cube. So the bit in the dashed box is effectively stuff inside the data cube, and then everything on the outside is how we view how things are connected. So on the left we have data coming in from various satellite sources. In this concept we deal primarily with analysis-ready data, and there's an activity within LSIVC looking at Card4L, so that's CEOS analysis-ready data for land. And there are other activities that are being looked at for SAR and so forth. That's about getting your data to a form where the observations on the pixels are actually geophysically comparable. You should be able to compare an optical satellite type for Landsat with an optical satellite for Sentinel-2 and use those two data together. You shouldn't have to use them. Consider that they've got totally different calibrations and so forth. That's the objective. I'll leave the scientists to figure out how much uncertainty is involved with actually achieving that goal. So that's where the data comes in. We call that the ingest process. On the other side, on the right, we have two different classes of users that we're dealing with. We have the users that are actually people who program. That doesn't necessarily mean they're a computer programmer. They may in fact be a computer programming literate Earth observation scientist, so they've got a background in Earth observation science as opposed to computer science, and they use the DataCube's application programming interface to do their work. And another class of user we have is your end user. I'm the person who wants just the map on the screen. I want the pretty graphs. At one level, I want to be able to trigger some form of analysis in an area that somebody else has already prepared for me, and I can just push that button. And we actually make reference to two different forms of analytics. There's the analytics in the, I want to do a continental processing scale and I'm prepared to wait 4 hours to get a result for Australia. Or it might be exploratory data analysis. I'm working with a smaller amount of data, but I've got a whole range of algorithms I want to try. I've got interactivity involved, and I'm actually being quite interactive with the data. So you've got your, in a computer science sense, you batch processing, where you're queuing up things and just waiting for results, and the other one is the fully interactive version. And the data cube is designed to operate with both of those modalities. Right? In addition to that, we have a couple of other additional service interfaces in the system. One is a replication service. In Australia, we host The entire Australian archive for Earth observation data is actually hosted at our major supercomputing facility at the NCI, the National Computational Infrastructure. That's a lot of data, but in order to do our science, quite often we will do that on our laptops or our workstations or even in the cloud. And so the ability to replicate a portion, a subset of the data cube into those other environments has proven to be an important process, and we're in the motions now of making that a more intelligent managed service interface. At the moment it's not very intelligent, but we'd like it to be a more intelligent one so we can maintain synchronization and even just awareness of the fact that this sub-data cube exists. We also have discovery and delivery services being developed to allow support web browser and web mapping type access to the data cubes, data and resulting products, and some of the analysis. So you can trigger analysis from your mobile phone and so forth. Both of those are in varying levels of maturity at the moment as we're developing them. So if we dig a little deeper and look at the next slide. So on this slide, we can actually see the notional architecture for the data cube. It's a typical layered architecture model. At the top, you have all your user interfaces. They're not the data cube. Initiatives build those. Initiatives like the one Brian just spoke about earlier, where there are many different kinds of user interfaces. Then we have your various applications and platforms and business processes that work underneath those applications. Again, they are not the data cube. Everything under the dotted, well, between the two dotted lines is actually the data cube core code. That's what the data cube is actually doing. So there's a number of components to that. Again, these are in various levels of maturity. I'm actually going to start at the bottom and work my way up because that's more or less how we've been developing this thing, and it is a good sign of the maturity. So in the data cube, a data collection, so a set of satellite data is indexed, and create a number of multi-dimensional storage units are created. So effectively, that'll be the equivalent of your relational database with all of your metadata and so forth in it, which describes your individual storage units, which may actually be files, or they may in fact be objects in, say, an S3 object store on Amazon. And that comprises a collection. A data cube is capable of having multiple collections, so you can have a Landsat collection or a Sentinel-2 collection and so forth. Primarily in a data cube, a collection will all be the same, particularly spatial coordinate system and size of pixels and so forth. They'll be compatible, and that's so that within a collection, the pixels line up over time. All right, so that you can assume that there is a consistency about how the data lines up over time. And that enables performance for within a single collection to be quite high, because that assumption is true. Above this index and multidimensional storage units things, you don't actually want to see that even as an application developer and a computer scientist. You don't really want to know about that on a day-to-day basis. What you actually want to know about is I can query that data and I can get arrays. And so we have a storage query and access module, which actually allows you to simply say, I would like Landsat 5 and Sentinel data over this spatial area and this time period. And when you ask for that, the data cube will go and figure out what data it needs to retrieve. All right? And then it'll place that in memory, and that it'll be sitting in memory, and it'll be an n-dimensional array sitting in memory for you, ready to use in your computation. And so that's actually the magic of the data management in the data cube, is really that part, hiding away the literally millions of files that make up particularly the Australian archive, and allowing you to just do a very, very simple query to get the subset of the data that you're interested in into memory, and then you can use Python as a programming language and all of its associated libraries. Those n-dimensional arrays are fully compatible with NumPy. They're standard everyday arrays, and as a result you can use the entire Python ecosystem of machine learning and image processing and computer vision and you name it, Python has it, tools to extract information from your data. I did miss a little box on the right. There's an ingester module which is used to actually populate that index and that multidimensional storage unit. The ingester works where you point it at the data that you're interested in pulling in, and it will suck that data in and put it in the storage unit. We'll come back to that a little bit more later. Above the n-dimensional array interface, we start getting into some of the other things we need to be able to do. We have prototypes for some of these. Web services for doing OGC web mapping services have just started to come online. We've got tools that enable you to specify some band math. I'd like to do an NDVI calculation. You could quite literally type in x minus y divided by x plus y, or whatever you want to do under it, where x and y are bands. And then say run that on multiple cores or on my cluster, and it'll actually parallelize some of that code for you automatically. That stuff's quite early days yet. The prototype that we had a little while ago was doing it quite happily. We're still working on a production version of that now. So if we look at the next slide. All right. So this is typically the flow of information or the flow of requests within a data cube type environment. This slide's coming up correctly. That's good. So your client application code will supply, say, some band math that it wants done or a function it wants run against the code. The user, again, you will supply the volume of data that you're interested in, its spatial location, its time ranges, and so forth. In the fullness of time, this is not quite implemented yet, but we have this in prototype. This will create a workflow that you want to operate. So you may say, for example, if you ask for an NDVI type calculations, that's very simple band math, but you want to process it on Australia. You need to be able to run that in parallel. And so the magic in the middle blue blocks there, the analytic engine, the execution engine, and so forth, this is doing things like it'll interrogate the data cube to find out, well, that volume of data you just asked for is Australia. That's 500 terabytes of information. I can't load that into the RAM in a single cluster node. So what I will do is I'll get descriptions of that, and it'll work out, look at that data and say, okay, to process that data effectively, I can divide it up into smaller chunks on 1,000 cores, and then it'll feed it off to the execution engine, which will marshal the cluster to get that work done for you. And in that process, it'll divide up how much data each cluster node gets and allow that processing to occur. And if you hit next slide again, you should get a slight change in the diagram. Yep. What's happening underneath, of course, is the data management and access module is allowing for the retrieval. It's making transparent the retrieval of that underlying information. But the thing I wanted to note here is the index store is providing a lot of information that allows for planning of execution, because it tells you about what volumes of data are available, how that data is laid out, and what size the underlying storage units actually are, and so forth. So it works out how to divide up that data, and then you've got actual data being grabbed by individual clusters as required. So there's a lot of metadata in the database that allows you to plan execution should you use it, and so forth. Now, if we skip along a little later, the reason why that matters is because we don't want our scientists, this is a typical CSIRO scientist in the middle there. Yes, that next slide, please, thank you. The one with the green, that's it, thank you. Really what we want to do is get our CSIRO scientists, yes, they all look like that, they're all mad, and that is a gender-neutral picture of a CSIRO scientist. The n-dimensional array interface that we want the scientists to see really should be a case of they specify the data they want to analyze, the analysis functions they want to run, and the resources to use. And then they push go. We don't want them having to figure out how to run that on a cluster, run that on a cloud, run that on a HPC system, deal with Lustre file systems, deal with S3 object storage, and so forth. They should be able to effectively write, particularly for relatively straightforward algorithms, a simple piece of band math and have it run on any of those platforms. And in the CSIRO case, that's important because we want to be able to go from a PC, desktop level kind of laptop exploratory data analysis, figure out an algorithm, and then say, run that everywhere in Australia on the big supercomputer without having to rewrite the code, because that's very inefficient. So, and the use of NumPy and Python and Xarray here is in order to make, well, Python's just very useful for those types of scientific endeavors because of the additional libraries that are available to work with Python as well. So again, we expose this as a Python interface. If we take a look at the next slide, a lot of people get interested in how the data is actually organized within the data cube. It's actually relatively straightforward. There should be a movie on the right that's displaying, it's not appearing on mine, but we'll just avoid the movie. The movie's not very exciting. You can look at that. The files will be available for download afterwards, so you can have a look at that. The data structures are very simple. The data cube can index files as they currently exist on a system. So if you've got a bunch of GeoTIFFs or whatever, you can just index them natively and not dice and stack them. But it can also dice and stack them. And so what it'll do is it'll make sure all the pixels are lined up, and it'll make the storage units a uniform size and shape. By doing so, you actually improve execution performance a little bit down the track. If you simply index some data that isn't consistent, then the data cube will in fact reproject on demand during the middle of calculations. Suffice it to say that is not very efficient. But it can be done because there are some circumstances where you don't have control or can't actually replicate the data archive. And that's quite important. So it really is a simple case of getting all of this data calibrated to the same, in this case, surface reflectance levels. So that's the reason why we do analysis-ready data, to have it spatially aligned, so you can actually make that assumption that this pixel on the ground is the same for all of the time samples that I have all the way through it. We also do our best to keep every observation and to track its provenance through all the processing stages. So there's a lot of rich metadata about how the data comes together. If we skip along a little bit further, to the next slide. Thank you. We've recently added, beyond the file support, we've actually added a native S3 driver for use with the cloud. So we now have two back-end drivers for storage. The file one effectively uses multiple file formats. It uses GDAL. We prefer the use of NetCDF. That can be on a file system like Lustre or a POSIX file system, or it can be at the end of an HTTP request. So it might be something like an AWS S3 endpoint. That is still a file at the end of a HTTP endpoint. And each of those files can be multidimensional in space-time, bands, masks, attributes. It's actually configurable how you do the chunking for that. When you do ingest, you can actually configure that. It will be consistent for an entire collection. The native S3 driver is an exploratory piece of work that we've been doing at CSIRO. In this particular case, we're not using files, we're actually using objects. They're actually effectively a sparse array representation in S3. The reason we can use a different approach here is there is effectively no limit to the number of files, or the number of objects, that should say, in S3. On the file systems at CSIRO, on the NCI, we've actually hit the inode limit for the file system, so the number of files we can have in the system has been hit on a number of occasions, depending on how we divide up the data. So there's a tendency to need to group data, time and bands, to reduce the number of files. On S3, we don't have that issue. We can actually have inordinately larger numbers of objects in S3, and it will scale effectively. The other thing this enables on S3 is we can do parallel I/O to single objects. And given the way S3 operates, there's higher latency between a compute node and the S3 storage. Having multiple threads running dramatically increases your throughput on doing reads. And so this driver actually runs parallel threads to do reads into the memory array. If we look at the next slide, that's just a bit of imagery around how it operates. As you would expect, The data is indexed in the usual way. We actually use the same indexing mechanism with a couple of little extensions as is used for the file-based system. And then we divide up the volume of data into a lot of smaller objects. When it's reconstructed, we actually parallel retrieve that data into shared memory on the node at speed. And we're getting much higher performance through this, although we're still experimenting with to see if we can get that even faster than it currently is. The interesting thing is it continues to scale. As far as we can tell, adding EC2 nodes, this thing will just keep scaling linearly within the data center, which is kind of nice, to say the least. And next slide, I think. We're nearly there. The other thing I wanted to make a note of is the data cube is quite often used in a PC single server environment. It's also used on a HPC system. The picture on the left is actually Rajan, the computer at the National Computational Infrastructure System. It's 57,000 cores. It's quite grunty and runs quite well. But we've also got the cloud EC2 and S3 with the native I/O, as I just mentioned, actually running. One of the reasons why we wanted to be able to do the cloud support is because CSIRO is looking at setting up an Earth Analytics Industry Innovation Hub for the local region, and that will the industry doesn't have ready access to the NCI facility for a variety of reasons, but they do have access to, of course, to Amazon. There's also an entire industry ecosystem on Amazon of other services that can be added to. So we're looking at setting up this industry innovation hub, not because we particularly want to provide massive numbers of Earth observation services, but because we want to accelerate the rate at which our Earth observation innovation can actually be used by industry. So by putting our technologies directly into that environment, we're hoping to skip a few steps for industry use and encourage market growth. And we've had done a lot of market research in that space, talking to our clients and our potential SMEs and spin-offs, and they're actually very interested in this concept and being a part of that innovation. So really that's it. The next slide's the last one. That's a bit of a quick overview of what's underneath the data cube. And I think I will leave it there. Thank you.
Thank you very much, Rob. That was great. Now we've got a number of questions that came in through the audience, and Jennifer is going to moderate those.
Okay. All right, so the first question was a bit early on, and the question was from Franklin Z. Can you ask Brian if there have been any ground validation activities associated with some of the processed products? For example, percentage water per pixel.
Yeah, the answer to that is yes, some of that has been done. In 2015, GA performed ground validation for the WAFS algorithm, which is the water detection algorithm. They actually wrote a paper in Remote Sensing the Environment, and they showed that the algorithm was 97% accurate in Australia. Unfortunately, there have not been ground validation test cases outside of Australia, so that is something we would like to do. And concerning ground validation in general of our algorithms, we're working with a few other potential examples like Dahlia Kirschbaum at NASA Goddard for landslides, working with the GeoGlam project on fractional cover testing at their RAP test sites, and then there's some interest in World Bank for coastal change and water quality. So I would like to have a lot more, Frank. Unfortunately, we don't have enough yet.
Okay, thank you, Brian. The next question is, how does AGDC document data quality and convey it to users?
Rob may have an answer for this, but I will say that data quality can easily be part of the metadata when you ingest. So upon creation of the data cube, you can pull in any of the metadata you desire, so you can always put a quality tag to go along with it. Anything you want to add, Rob?
No, I actually, the only thing I would add is that particularly Geoscience Australia had done an inordinate amount of effort in tracking provenance through the data cube in the metadata. And we're trying to progress that all the way through to when you add your own derived products, like a fractional cover output, you can actually continue that provenance chain all the way through to address the issue of quality. I mean, quality, of course, is in the eye of the beholder, how you use that. So it's really about tracking that provenance through, and there is quite rich metadata. We actually don't use a relational database model anymore. We actually use a document-based model, even though it's still with PostGISS in our environment. And that is to provide that flexibility around the metadata and how we track particularly provenance information through it. Hopefully that answers the question.
Okay, thank you, Rob, and thank you, Brian. Next question is has a comment as well. A curiosity from my side, and I don't know if it is out of scope, but define today the components / metadata attributes of the analysis-ready data to be implemented in a data cube could affect the use of the same data cube in the future when the user needs could change. And then the second part of that, I don't know, maybe you want to take that piece first, but the second part is, could an update of the ARD in a stable data cube represent a significant effort?
So we've done...
So what
Go ahead, Rob.
I was going to say that in the Australian environment, updating ARD actually happens a little more often than we anticipated. And replacing the entire Australian archive is a significant effort. And so this relates to the data preparation and processing as opposed to the data cube implementation itself. This is to do with that ingest process. This is the reason why the provenance is tracked in the metadata. So there is a data management process around the collections that we're maintaining in the data cube in Australia, and that when you get an update coming through because there's been some change in that processing pipeline, the atmospheric correction or some other new piece of calibration information comes through and we can update it for good reason, then the entire archive will be updated. But users will know that because the provenance tracking is there. And we're looking at providing an ability to possibly even access, usually off of tape, some prior versions of the data cubes if you need to do a compare and contrast type environment. So a lot of that, I think, is answered by around the issue of how you deal with provenance. So over to you, Brian.
Yeah, all that is good. I will echo and say that we've had similar experiences with Columbia, which has recreated their data cube already a second time due to a change in analysis-ready data. And we see it in Landsat data all the time. Anytime there's a new atmospheric correction algorithm or some significant change in the data, their entire archive gets updated. So it's really up to the user to understand what the change is in the ARD and whether or not it's worth the effort to re-ingest the cube and recreate it, because there is certainly an effort involved.
Okay, thank you both. The next question is, what are the differences between data cubes and off-the-shelf array databases? Is this only limited to gridded data? Can it handle swath data? How does it handle projection, resolution differences? And then how is the data chunked on the cluster? Doesn't chunking strategy depend on the query set? If you need me to repeat any parts of the question, let me know.
So I'm guessing Brian's going to say, Rob, over to you.
Yes.
So Rahul, it's been some time since we've spoken, Rahul. I don't know if you remember, but we caught up at an AGU conference several years ago. So the difference between data cubes and the array databases, implementation primarily. It's just an alternative way of tackling very similar problems. My take on this is literally I would view this as this is just one of a number of implementations attempting to deal with the issue of how you process Earth observation data. We did do some comparisons in the early days when CSIRO first got involved with working with GA and their prototype version 1 version, when we looked at SciDB, Rastaman, and GeoTrellis and a couple of others that all are out around that time. This is several years ago now. Of course, things will have moved on. And we did the comparisons there, and there were a few things that we at CSIRO, we preferred about the way in which the approach that Geoscience Australia was starting on, and that we continue to work on and improve upon in the current implementation. The strong use of Python was one. The ability to work with IPython notebooks and so forth is very, very suited to our science environment and type of innovation doing. It is limited only to gridded data, but that was actually one of the pluses, because it made dealing with the data relatively straightforward, and the way in which we're looking to improve the interface is effectively everything looks like underneath a NumPy array. And that way, our Earth observation scientists doing their algorithm development are actually working with a very consistent environment. We also like the fact that you could run it on your PC, or you could run it on an HPC, or you could run it on a cloud. So that ability to deploy across those different environments relatively straightforwardly was also, again, so that we can keep our scientists engaged very effectively. Can it handle swath data? This all comes down to projections and resolutions. Effectively, the constraint is that a collection in the data cube should have a consistent projection and approach to the data, and that pixels should align over time. So the same point in space should align over time through all of the different chunkings that occur within that data set, within that collection. Across collections, that is less true. We did have a stage at one point when we were looking at using what would be referred to now as a discrete global grid, and having all collections being the same projection. This was a little bit problematic for some of our use cases, because this data is used not only in the data cube environment but also for other purposes, particularly on the NCI. So we can't just put all of the data files in, all the NetCDF files, into a raster database or some other system. They actually have to be natively available on the NCI as files. And that's part of one of the challenges we've had with developing the data cube, is that we are working in a shared environment. So we don't have room for 2 copies of the data, or in fact, we'd need about 6 copies of the data to keep everybody simultaneously happy. So the data cube's ability to index existing data or to use the same structures of data enables other applications to continue working. So applications that don't use the data cube environment but still use the data underneath. So that's another driver for the different kind of implementation here. In terms of the data chunking on the cluster, so there's 2 different kinds. There's the S3 driver and the file-based one. The file-based one, in the NetCDF environment, on ingest, you can specify the type of chunking you want internally to that file. You can also specify the dimensionality of the actual gross NetCDF file, how many pixels you want, or how much surface area and how deep of time you want to do. We've run a variety of experiments on how those affect performance. They are very much dependent on the types of queries and processing that people want to do, which is why we've made it parameterizable. But generally speaking, we're not aiming to achieve highest performance, but a sufficient performance to support a very wide range of applications. So we're not talking about tuning to the nth degree for a specific application in most cases. I probably ought to leave the answer to that very complicated question at that point, but hopefully that gives you a bit of an overview.
Okay, thank you, Rob. The next question is, following up on Rahul, the question's from Peter Bowman. Open Data Cube is entering a field very recently where several Data Cube technologies are already available. For example, Rasdaman is running operational Data Cube services exceeding 500 terabytes and going to offer 170 plus petabyte Data Cubes in the near future. How do you relate to the state of the art?
I'm assuming this is the Peter Baumann of the Rasdaman fame. Peter, I have enjoyed looking at your work involved. I have to say, you've done some incredible stuff with Rasdaman and indeed the OGC standards to go with it over the last few years. So we reviewed RASDMAN in particular at the start of this process. So whilst the Open Data Cube, you've suggested the Open Data Cube has entered the field here, we actually entered the field several years ago with version 1. I think what's happened more recently is we've become visible, a lot more visible, as one of a number of implementations in this space. And I actually, in preparing for this webinar with Chris Lyons, Chris actually mentioned at the beginning he was a bit of a Data Cube skeptic. I think that's a very healthy view to have. I'm still a Data Cube skeptic. I'm not convinced that the approach that we're currently taking is the best way to do it. And there are a number of other entries into the market, including commercial offerings from people like Digital Globe with their GBDX platform that are popping up. I think we're still to see a lot of shakeout from here. I think what is very important to note is not the different styles of implementation or how they compete and so forth. That's one thing. What is really interesting to note is the fact that the engagement level is high. The interest from users, as Brian has pointed out, is actually quite high. The interest we've had in our Industry Innovation Hub is quite high. And I believe the reason that is high is because the message of the Data Cube, the promise of removing this common pain that everybody is suffering, that they don't really need to deal with, the ability to write a simple piece of bandmath and have it run in parallel on a global data archive, those types of promises, which a lot of these technologies can actually address, are hitting a chord and resonating with end users. All right. We've been with the Open Data Cube. We're currently sitting on the top of the hype curve in terms of people being aware of what's going on. And I think there's still a lot of work to be done with regards to which of the technologies is most appropriate for which types of deployments people are doing. RASDMAN is quite useful for some things. RASDMAN is actually installed at the NCI alongside the other data cubes. In fact, it can actually use the same data sets that we've got for the Open Data Cube implementation there. I'm not going to comment on the experience that NCI have had in doing that because I haven't been personally involved. But it has, both are running, and at the moment the preference is still to use the Open Data Cube implementation for a number of reasons which aren't generally related necessarily to scalability and performance. They might actually be related to the simplicity or the ability to move from one deployment platform to another. So there's other factors that kick into play. So hopefully that gives, again, some insight into that question.
Great, thank you. This is obviously not Jennifer Brennan. She had to take off. As all of you know, we had a massive power failure here, so we're running a little bit late. But for the next question, for Landsat, how do you handle that cross-UTM zones? Or do you always use a national map projection so everything lines up spatially?
So in the Australian Data Cube, we're operating with an Albers equal area projection. So there, it's a national projection, effectively, so it lines up spatially. You could index data. I'm thinking out loud, so this might not. I've not tried this. You should be able to use data that is in different UTM zones, and it should reproject it on the fly for you. I haven't tried that, so I don't know if it actually does work, but theoretically it should. It will go slower when you do that. But generally speaking, we use national projections, in this case, Albers equal area. There's also been a lot of work done on discrete global grid systems and a standard for that with the OGC. You can actually go, if you go to the OGC website, you'll see this WGISS, discrete global grid system. That's actually being driven in part by GA and their interest in this particular issue.
Rob, we actually lost you for about 30 seconds, so can you repeat what you were saying at the moment?
Yep, sorry, is this better? You can hear me okay now?
Yes, this is fine.
Okay. Yeah, so what I was saying is you theoretically could use the native UTM projections, and the Data Cube should be able to reproject it on the fly. I haven't tried it, but that ability to index existing files should allow that to happen. Generally speaking, though, we do use national map projections, and there's a lot of work done by GA on discrete global grid systems, and the OGC standard for discrete global grid systems recently got approved. And again, to address this type of issue in these environments where effectively you want to just treat the entire globe as a single entity as opposed to having to deal with projections any longer.
Excellent. Thank you, Rob. The next question, I'm very curious about the concrete interface. Showing some working code examples would be much appreciated.
Okay, Peter, you can find some ODC, Open Data Cube, IPython notebooks on the GitHub repository. And in the end, it really comes down to datacube.load, which takes a specification for which sensors you want to deal with, and volumes of data and bands and so forth. And then after that, it effectively looks like NumPy arrays. But there's definitely some example code up on there. I didn't get into details in here. It's certainly not as sophisticated as RasDemand's RasQL type interface. But again, this is a case of our preference here is to expose a very familiar Python environment, because we find our Earth observation scientists can engage with that quite rapidly. And they also get to use all the other lovely Python libraries in a very consistent manner. But definitely there's some on the GitHub, and hopefully we're going to have a community forum for the sharing of implementations and algorithms that people can actually just share as part of the Open Data Cube community more broadly.
Excellent. And next question. How do you assign digital object identifiers to ARD? Do you assign a data cube as a whole or to parts of it? How would one cite data one gets from the data cube?
I really want to dodge answering this question, and the reason for this is it's a very important question. The guys that are best to answer that are the guys who deal with the provenance metadata, because it has to use this, it has to address this issue. That's the guys in GA. They've done a lot of work on these particular issues. I'm not completely across it, so I prefer not to answer that, attempt an answer to that question, and instead defer you to the guys at Geoscience Australia who've done a lot more work on the provenance system. I do know they have been looking into this, and I do know that some of them have grey hair and they're still relatively young from having to think about this particular problem, especially if you're dealing with just subsets of the data cube. There is another related piece of work that you may or may not be aware of, which was done by a joint working group on linked open data for geospatial work between W3C and the OGC, looking at linked data representations for data cubes and Earth observation data in particular, and how you can represent, effectively it'll become a DOI, that ability to address subsets of data that are indeed versioned, which is what you need to get to the kind of DOI level. That report is published on the OGC website. I'll try and work with Jennifer and so forth afterwards to put a link somewhere on the system where you can grab that information and go and have a look at that piece of work. But it is definitely a work in progress, and I would refer you to GA in that regard.
All right, thanks a lot, Rob. So that was our last question. I'm sure that we can have some follow-up questions on our various email lists if we so desire. And I want to thank everybody for hanging in the face of our local thunderstorm here and the technical difficulties. And I really
Anybody out there? I think we've lost connection.
Yes. Yeah, I think we are on our own.
I think we've lost
something just
connection
happened.
to
Yeah, I think we're on our own. So.
Okay.
Okay, Chris left the room.
Okay, well, yeah. Thank you so much. Thank you very much.
That was really good.
That was really great. We will put the recording,
Great, thanks, Jansen.
the URL to the recording. That's going to be on the YouTube channel and the presentation file,
Fantastic.
on the WGISS Tech Expo website.
Okay. Thanks, everyone.
Thank you.
And
Bye now.
so that people who couldn't come can play that back and see it. Okay, thank you very much.
Thank you.
Right, bye.
Bye.
Cheers, everyone.
Bye.